Well, this is a joint work with my colleagues Gonçalo Jacinto and Patricia Filipe. And it's about the growth of individual animals living in a randomly varying environment. And by environment, we mean the internal environment of the animal, the external environment that affect the growth rate along the lifetime of the animal. And then we have an application to the optimization in cattle raising. And I just want to present it some overall picture of what we can do with this kind of stochastic differential equation models, which are an alternative to the classical regression models that have been used. And we have all the artillery to apply them in real situations. That's the main point of this talk. So let's start with some introduction, then we'll talk about the growth models for individual growth. The individuals grow in size from birth to maturity. And then we'll talk a little bit just about parameter estimation issues for the models we're going to use. And then for the application to the farming situation, we'll talk about the profit structure, the costs involved in raising the animals, the price they get when they sell the animals to the market. And it's a complicated structure. Some years ago, we did the same thing with a very simple structure, fixed cost per kilo, things very simple. But actually, things are much more complicated, and so we'll talk about a little bit about that and how you still can handle those mathematically without, well, with a little bit of fuss, but not really without any difficulties. And then, of course, with the profit structure, we have a profit, and we want to determine the mean value and the standard deviation of the profit. And finally, we apply it to the real situation with data from a Murtelengo breed, which I'll show you later. And since we use in the computations, we use the parameters obtained by estimation, by maximum likelihood estimation, they are not the true values of the parameters. So you want to check how sensitive are the results to variations in the parameter values. So the sensitivity analysis was performed, and finally we reached some conclusions. Well, let's talk motivation. Well, we want to model the growth of an individual animal living in an environment that is subject to random fluctuations in the internal conditions of the animal and in the external conditions. And those fluctuations in the environment in which the animal lives are going to influence the rate at which it grows along its lifetime. So we use stochastic differential equations to describe the evolution, in this case, of bovine weight, but it could be applied to other animals as well, of course. The theoretical part is going to be about optimization farmers' profit under a very general and realistic and complex market structure. The second part is an application to bovine males, PDO, which are denomination of origin, protected denomination of origin, PDO bovine males of two breeds that live in the region I am from, in the Alentejo region of Portugal. And they are, they are raised in the fields like that. We have two breeds, the Alentejana breed, which is under this association of producers, and this is the Murtelengo breed, the ones here, this breed here. They are relatively small animals, and this is the association that handles them. And this work involves a lot of people from the zootechnical department, research institutes in the veterinary sciences, producer association, and so on. It's an operational group, GoVolve Plus, which is funded by PDR 2020 by European funds. And we did, this work is a piece of that overall operational group. And we used the results we obtained, I'm going to show you today. They were used by RuralBit, one of the partners of this operational group, to develop a web tool that farmers can use to determine what is the optimal age to raise, to sell the animals to the market. Okay, let's look what is typically done when you're talking about animal growth. Growth of individual animals is to use regression models. That's the classical thing. Regression model is basically you have a kind of deterministic growth curve that you think the animal follows along its lifetime, since its birth until its maturity size. And then there's, of course, what you observe is probably not exactly on the curve, is a little bit above or below, so some error. And that's the typical model they use, regression. Of course, that would be fine if the errors were due to observation errors. I mean, the scale in which you weight the animals is probably not very precise. But that's not the issue here. Our scales are quite precise indeed, so those errors are negligible. The differences from the curve are due to environmental changes that affect the growth of the animal. So if you use regression models and you want to make predictions, you have a problem, because you're assuming all animals have a common with this curve, and the deviations are just from that curve. And the current size of the animal is irrelevant, because if an animal is much below the growth curve, the deterministic curve at a certain age, and you want to predict the size of the animal tomorrow, it will be the size of the curve. Of course, it cannot grow in one day that fast, because it's a dynamical process. So these models have these problems. I'll show you some trajectories of a test group of 18 animals that were raised, financed by this project, and to get the data. And they were raised, from birth until 24 to 30 months of age, depending on the animals, and regularly weighted almost every month, not exactly but approximately every month they were measured. These are the trajectories, 18 trajectories. You see, I mean, there are no miraculous recoveries in a small time. So the regression models really do not apply. This test group was from PDO to Lango males. I'm talking about males, of course. These things can be applied to females, but females is a more complex situation, because some females are left for milk, others for meat. So it's for reproduction too. So it's a more complex situation. And of course, they grow differently from males. So you have to have different models. The same model with different parameters, actually. Now, so the solution to that is not to use regression, but to use stochastic differential equation models, because they take into account the dynamics of the growth of the animal, and also they can take into account the fluctuations in environmental conditions. Okay, so we also, besides this test group of 18 animals, the one I'm going to use today for illustration, we also have more data, because the Producers Association has a database in which all animals of this breed are registered. Okay, and that's where Web tool is based upon, because they use the information. I mean, the farmer has an animal, he has a tag with its number, and he goes to the database, and he can collect information on that animal, and he can use it to make predictions for its future size. But I'm going to use the test group data instead of this one, because this one is quite heterogeneous. Actually, if you're just looking for males, there are females there too, looking for males with at least 3 weights along their lifetime, because if you have one weight, there's no dynamics there. You have to have at least 2 or 3. We choose the ones with 3. We have 16,000 animals in the database satisfying that condition. And we have these 16,000 animals have 96,000 observations. So on average, each animal has six weights along its lifetime. But of course, it's quite heterogeneous. Some only have 1, 2, 3 weights, some have 4. Even some of them have 33 weight. They have been weighted 33 times along their lifetime. And the ages ranges from birth to 0.2 to 16 years of age. So some animals die very early for several reasons. Most of them go to the meat market by 15 months of age or around that. And some of them are kept for reproduction purposes, so the bulls. And those, of course, live longer. But they're very few and are not typical animals, because they're chosen, especially for that purpose. So they are better animals in the sense of the production point of view. So they are not, typical of the. So these observations will bias the results. Furthermore, we have only very few observations over 18 months of age, very, very few. So the maturity size of the maturity part of the growth curve doesn't show up, which makes the results biased. Okay? And also not only in mean value, but also in the variance estimation. So you have to use correction techniques for bias and the variance. And we have adjusted those techniques to this type of situation, using using several techniques like bootstrap or using weighted maximum likelihood, in which you weight according to the age, give more weight to later observations because you have fewer. And we will optimize that too. But I'm not going to talk to you about the statistical work we've done. That's quite substantial, but not today. So we're going to work with this test group data because the animals are weighted regularly along their lifetimes, and they go up to a later age, 24 months of age, some even to 30 months of age, which is not still the asymptotic age, but it's closer. We didn't have financing to go further on. Okay. So let's talk about the model. Denote by x of t the size of the animal at age t. And for size, here in the application, we're going to use weight, but it could be some other size. And then we follow an idea from Garcia, which instead of working with the actual size of the animal, we work with a modified size, yt, which is a transformation by some function, nice function, strictly increasing C1 function, of the actual size x of t. And in so doing, we can use a very simple model, this one. Well, forget for the moment about this part, which takes care of the environment of random fluctuations. Look at the deterministic part of the equation, and you can see that it just says that in a small time interval dt, the change in the modified size of the animal, the transformed size of the animal, is proportional to the difference between the current size, the current transformed size, and some asymptotic size or maturity size. Okay? And the rate of approach to the maturity size is given by this beta. Okay, so a very simple linear model. Okay, well, of course, we have some initial condition. Okay, at an initial time t0, that may vary from animal to animal, we weight the animal and have a measurement x0, weight x0. Okay. And now y0 is just a transformation by the function h. Okay, so that's the initial condition. Well, the trick is on the function h. With different functions h, we can recover the classical models that have been used with regression, unfortunately, but that have been used for the growth of the animals. Okay, because if you solve the deterministic equation with these functions, you get the different growth curves that have been classically used in the literature. Well, I have some examples. Well, depending on the function h, you have Mr. model, you have the Buttel-Amphi-Riches model, you have the Gompertz model, which is actually the limit of this one once it goes to 0, the logistic model. Oh, sorry, there's a minus here that should be there. This minus is wrong. I forgot. Sorry, just forget the minus. Okay. So, of course, this asymptotic maturity size alpha is just a transformation by function h of the actual maturity size a. Call it a. Okay. What about the stochastic term? Well, I'm assuming the process y, the transformed size, is following on the average this deterministic rule of growth, but there are some deviations from the main growth rate, which can be approximated by white noise. And so when you talk about the increments of those changes, they are the increments of the integral of white noise, which is the Wiener process. Okay, and for that we use the standard Wiener process Wt multiplied by a parameter sigma that somehow measures the intensity of the environmental fluctuations, or better, measures the effect of the intensity of the effect of environmental fluctuations on the growth rate of in terms of the transformed size. And of course, if you have different animals, as we do, we assume that they correspond to independent trajectories of the Wiener process, independent realizations of the Wiener process. The model is very simple, as you see. So you have a linear stochastic differential equation. So the solution is a homogeneous diffusion process with the drift coefficient equal to the deterministic part of the equation. So you can see drift coefficient is that one there. The diffusion coefficient is just the square of that. So you have the drift and diffusion coefficients, and you have even an explicit solution of the equation, which is given by the deterministic part plus a stochastic integral multiplied by that. Okay, stochastic integral with respect to the Wiener process. And this is Gaussian. This is deterministic in this case. The integrand in this case is deterministic, so the integral is Gaussian. So you know that yt, the transformed size of the animal at ht, has a Gaussian distribution with what mean? Well, the mean of this integral is 0, so the mean is just that, deterministic solution. And then to determine the variance, you have to multiply the square of that by the variance of this integral, which is the integral of the square of the integrand with respect to time. And so it's a deterministic integral you can compute. So the variance after some computations gives this value, and you can see asymptotically as h goes to infinity, and actually it doesn't have to go too far, its convergence to the asymptotic is quite fast. You get a Gaussian distribution with this, an average value, which is the modified asymptotic size, alpha of the deterministic model, and some variance around it, okay? We have also studied, but I'm not going to show these results today, mixed models, because different animals may have different alphas and different beta parameters. Okay. They may vary from animal to animal, according to some distribution, which we assume to be a Gaussian distribution approximately. And these differences among animals may be due to genetic differences. We can also model those things and account for those, but I'm not going to talk about that today. Now, as I've said, we had data, the heterogeneous data based on the overall database with 16,000 animals, but today I'm going to show you the test group data of 18 animals, because the data is more evenly spaced, doesn't have problems of bias, and so it's much more convenient to use it, and I don't have to waste time on the techniques of bias correction and things like that. Well, we're going to do it for the PDO Bertolengo males. We did it also for the other breed, the Valenciana breed, but we don't show it today. And I'm going to use two models, the log, in which the function h, the transformation, is just a log of x, of the size, and the other model, the Bertalanffy-Richards model, in which it's a power of the size. And actually the best power in terms of likelihood is not 1/3, but it's very close to 1/3. So we prefer to use c equal to 1/3 because it has a nice ring. I mean, the weight of the animal x is approximately proportional to the volume of the animal, and this is a kind of a linear dimension corresponding to that volume, 1/3 power. And it works quite well. I mean, the difference with the real one is quite small. So we have the maximum likelihood estimates, okay, for the parameters, for the Gompertz model and for the Bertalanffy-Richards model. Don't try to compare them, because since the function h is completely different, the parameters have completely different meanings, so they're not comparable. But I've converted the parameter alpha, which is the asymptotic size, transformed size, in terms of the actual size, so inverting the transformation h. This thing, I inverted that to that. For the Gompertz model and Bertalanffy-Richards model. And you see the prediction for the asymptotic size, on the average, is different for the two models. And that's because we have very little information on the upper size of the growth dynamics, the growth curve. We have very little information on the upper size. So the precision of the estimation of maturity size is not that good. We might think, well, maybe which model is better, Gompertz or Bertalanffy-Richards model? Actually, they perform almost as well. The Gompertz is slightly better in terms of likelihood, but it's a minute difference. Okay, very minute difference. If we have more data, maybe we could tell them apart. but it really, in this case, it's not. Well, I still prefer the Gompertz model because it's slightly better, but the difference is minor. Okay, so let's talk about the profit structure, the costs and the selling prices of the animal. Of course, assume a farmer that has an animal with an HT0 that he bought, or maybe he already has, but he wants to know what's going to happen from now on, T0 on. Okay, so the animal has HT0 and he wants to raise it to up to some HT in order to sell it to the market. What is the optimal age to sell it in order to maximize the expected profit? That's the issue. Well, of course, the profit, if he sells the animal at HT, is just the difference between the selling price of the animal at HT and the costs of raising it up to HT. Actually, I think that these slides are the old ones. I'm sorry about that. These are not the slides I intended because we had a technical problem when we have to switch to another pen, and unfortunately I switched the wrong file. Okay, but so there was more information on the slides, but I'm sorry about that. Actually, this was done, well, no problem. I'll try to adapt, but there was some mistakes here that you probably cannot reproduce. Well, the selling price or the income is very simple. It's just proportional, it's just given by the carcass weight of the animal. The carcass weight of the animal is the actual weight of the animal, xt, multiplied by a dressing proportion R. And why is that? Because a big part of the animal is not useful at all. So about 52% R is about 0.52. Okay, and so the carcass weight is some proportion of the actual weight. And then there is a price per kilo for the carcass weight. But unfortunately, the price per kilo is not just a constant. It depends on the age of the animal. And for each age, it will depend also on the category, on the size category of the animal. Actually, on the carcass weight category of the animal. But of course, if it depends on the carcass weight, it depends on the weight. So I just put a function of x of t, okay? So what we have to do, this is price per kilo, we have to decompose the space of the carcass weights into intervals, for each ht, into intervals, and in each interval, such that in each interval the price is fixed, is constant, okay? So let's denote by PTJ the price per kilo of an animal of ht belonging to the interval number j. And so the price per kilo is just going to be the linear combination of these indicator functions of the carcass weight, which we can write in terms of the weight itself, like that. Well, and you can see, actually, capital R, this R here is about 0.52 something. I have written the number there in the new slides, but here they are not, it does not show. And another thing, by the way, these numbers are pre-inflation boom, okay? Because now they change all the time. Okay, so almost every couple of weeks they change the prices. So, but these are the pre-inflation boom, so I'm going to use those. We have 4 categories of size, of ages, and for each category we have intervals for the carcass weight. Okay, this is the carcass weight. And depending on the interval, this is the price per kilo. And the intervals are even different from age to age, so they are not the same intervals from different ages. Well, what about the raising costs of the animal? Well, I put it here, this is wrong. There shouldn't be a function of xt, because it depends not on the xt, but on the whole trajectory, m to time t. Okay, so this I corrected, I took the xt here, because it depends on the whole trajectory. Well, but anyway, we have fixed costs, tax, sanitation, transportation, commercialization, and of course you may deduct subsidies if there are subsidies. And you should add the cost of buying the animal at HT0, which I'm not considering here, But it doesn't matter for optimization purposes. You want to say what is the best time to sell the animal, and that's a fixed cost. So at the end, you can just subtract that cost, okay? So it doesn't influence, and I don't want to put it in the application concretely because it varies a lot. So the farmer knows it, and he can deduct that cost at the end, okay? Then we have maintenance costs per unit time, and then you have feeding costs per unit time and unit weight, because the larger the animal, the more it eats, okay? So we have this complex structure. Now, let's show you just, actually we had to make an approximation. Now we have experiments that determine exactly how much, is the cost per unit weight, how much the animal feeds per unit weight. But at the time, the results are not yet finalized. There's another group doing it. So what we had is the animals were fed all together. So we don't know, and some are larger than others. So we just know an average value per unit time. And so we had to use it. So we assume that the feeding costs are also proportional to the time the animal is being raised. So since it's raised from HT0 to HT, multiplied by some constant C4, which is the price, the cost of food per day, per animal per day, then you get this expression. So you can join these two into one single constant, which is about that, was about that, is no longer about that, because the price has changed after inflation, was about that, and those are the fixed costs. Okay. But of course, this can be applied to other situations, other animals, other costs, so you have just to adjust the parameters. What is the idea then? Is to determine the optimal selling age, T, to maximize the expected profit. Okay? That's simple. Which is the difference between the selling price, the expected selling price, and the expected costs of raising the animal. Well, but of course you you also like to know not only what is the average profit, but how variable is that profit. So the standard deviation is also useful information, the standard deviation of the profit. So you can compute it like that, the square root of the variance, which is the variance of the selling price, the variance of the costs, and twice the covariance, minus twice the covariance. Well, and to obtain that, you have to use properties of stochastic integrals, because the solution of the stochastic differential equation uses stochastic integrals, so using those properties, you can get those results. So everything can be done, actually, that's the point. You don't have to use the regression models which are not really appropriate. Well, on trying to obtain the expected value of the selling price and the variance of the selling price, we come up with the first and second order moments of the size distribution of the animal at HT. That's the PDF, probability density function, of the size of the animal at HT. Okay. But truncated moments, because at different intervals you have different prices of carcass weight. So you end up with truncated moments of the distribution of XT. And remember, XT is not Gaussian. The transformed size YT is Gaussian, but XT is not. Okay, what about the costs of raising the animal, the expected value and the variance? Well, it turns out, after computations, things like that will show up. The integral over age, initial age and final HT, at which you're raising the animal, of the expected value of its size. And the double integral with respect to age of the autocovariance of the process X, which is a non-Gaussian process. Okay. And now you also need those things here. And in trying to solve that, you come up with this strange item, which is the integral over age of the autocovariance of the process, the size process into autocovariances using two ages S and T, but truncated according to the intervals to which the carcass weight belongs. Okay, and then after obtaining those results, you have to particularize those for the specific function h you are using for the transformation. For the Gompertz model is the logarithm, for the Bertalanffy-Riches model is c to power 1/3, and for other models you have to do it too, but we just did it for these two. Now, just to give you an idea, because I'm not going to go through all the details, but to give you an idea of how those things are complex. Well, that's the price per kilo, you remember that expression. That's the expected value of the selling price of the animal at ht, which is the price per kilo multiplied by the carcass weight, which is r times xt. Okay, and so it's given, and we want the expected value, so we come up with that. Of course, that thing is just the expected value, just the integral of this function multiplied by the probability density function of xt. But of course, this indicator function truncates the integral, so you have that. Here it is, the truncated first order moment. If you want the variance of the selling price, then you do some computations and you come up with that again, and with the second order moment, truncated second order moment. So you have to obtain these two quantities. Just to give you an idea how we do it. For the Gompertz model, well, you take advantage of the fact that the transformed size is the logarithm of the actual size. So the actual size is e to the yt. And yt, you know what it is. Yt, the solution of the stochastic differential equation, is Gaussian. And you know the mean at ht and the variance at ht. So you know everything about yt. It's Gaussian. So what you do, to obtain that truncated moment we need, we just change variables from x to y and use the density function of y, which is Gaussian. So everything we know, we know how to handle it. So this integral, is just given, well, so classical computations with the Gaussian, you get that. That phi is just the standard distribution function, the distribution function of the standard Gaussian. Okay? And similarly, you can obtain an expression for the second order moment, truncated moment, but I didn't write it here because it's a bit ugly, it's long. Now, let's look about the other model, Bertalanffy-Riches. Well, it's the same trick, you just use the transformation now is xt to the power 1/3, so xt is yt to the power 3. And you again convert that integral, change variables to y, so you have a third order truncated moment of a Gaussian, and that can be computed. It's a bit ugly, but it's feasible. No problem. What about the costs? That's for the price, selling price. What about the costs of raising the animal? Well, you just put expectations behind the expression, okay? And you get that. Using Fubini's theorem, you can exchange the order of integration here. So you have that. So you have to compute these things, which is not difficult, and then integrate with respect to h. But if you want the variance, well, I don't show you the intermediate computations, but you get up with the double integral with respect to h of the autocovariance of the process. Okay. So you need this thing here and this thing here. But let's first look at this, the integrand function, okay, what's inside the integrals. For the Gompertz model, it's not difficult. You just take advantage again of this transformation, and you can compute this and that. Okay. Here, it's a bit cumbersome. You have to use properties of the stochastic integrals, and then you have to integrate those two things to get what you need. And unfortunately, you don't have a closed form expression for that. You have to do it numerically. Okay. For the Well, just to show you how you compute those things, it's autocovariance is okay. You write it like that. And then you get that. And then this variance is the sum of the variances plus twice the covariance divided by 2, it disappears, so you get that. So you finally get that, okay? The difficult part is this covariance of the y process, which is Gaussian. But y process is the mean value plus the stochastic integral. This it is the stochastic integral that showed up in the solution. So these stochastic integrals have nice properties, so you can do it very easily. So these autocovariances, you can write it like that. Well, you end up obtaining when you're writing that, you have at obtaining the expected value of the stochastic integral at two different endpoints, two different end ages, u and v. Okay. Well, unfortunately, they are correlated. So you break this one iv into iu plus iv minus iu, which corresponds to integrals on non-overlapping time age intervals, and these are uncorrelated because stochastic integrals have that nice property. So the expected value of the product is just the product of the expected values. Okay, and then you can do it very easily. Okay, for the Bertalanffy reaches, well, things are a little more tricky, but no problem either. You just have a third order moment of a Gaussian distribution because this is a third power, and here you have a sixth order moment of Gaussian distribution, but bidimensional because you have two times, two h's, u and v. Okay, and they are correlated, of course, so they're not independent Gaussians, but you can write these things. And now, well, you do the same trick of decomposing the stochastic integral into two, okay, but now you have powers of power I and power j. There are some computations a bit more tricky, but still using the properties of stochastic integrals, you can get the result. I don't bother you with the details because they're just applying the properties of stochastic integrals. Okay. Now, what the covariance between the selling price and the costs, which you need to compute the variance of the profit. Well, it's not really very problematic. You just go over the computations. You would end up with quantities you already know, these two, and this new one, this truncated integral over h of the truncated autocovariance of the process x. Okay. And you can do it for the Gompertz model. I'm not going with the details, except now you have a bivariate Gaussian here, which is correlated, so you have to use the correlation. Still, well, all computations, but I'll save you from those. And finally, you get the final result, okay? Integral of that. Unfortunately, this has to be done numerically. You can compute what's inside the integral, but not the integral itself. That has to be done numerically, okay? For the Bertalanffy reaches model, you can obtain it explicitly, a closed form, okay? Now the trick, again, you have the bivariate Gaussian, you transform the x's to y's, you have a bivariant distribution, bivariate Gaussian, correlated bivariate Gaussian, and you know, we go all through the computations. You see, long time, long computations, and you finally end up with this thing, in which d is the integral of these, the integral of those quantities here. But everything can be done in closed form. That's the advantage. But let's show the application results, because that's more interesting. We applied to an animal with an initial age t0 equals 0.7 years, about 8 months, 8 point something months, which is a typical age of weaning. That is the typical age at which the animal starts feeding on their mothers and stops feeding on their mothers and starts feeding regular food. The finishing phase, it's called the finishing phase. And we use the initial size of the animal, weight of 170 kilos, which is the average value for that age. But of course, the farmer, when he uses the web tool, he can put their own its own values, its own age t0 and its own size x0. He can also change the prices per kilo and the costs of feeding if they're not satisfied with the ones there, because he may have a better deal or something. So you can change the values. But there are some default values in the web tool. Now, let's plot the expected profit as a function of the age at which the animal is sold. But for the Gompertz model is the red curve, for the Bertalanffy reaches model is the blue curve. And you can see that the optimal value is reached at 1.25 years of age, 15 months. That's the best age to sell the animal. Well, the break here is due to the changes in prices. Okay. At the age 1.25, the prices change. Okay. So actually, the farmers are selling the animals on the average about this age, a month earlier, getting a profit which on the average is about 10 euros below the optimal. Okay. That's not too bad. They know how to do things, even without models. Okay. And that's the standard deviation of the profit for the Bertalanffy-Riches model. That's an example. Of course, you can change different initial conditions and get the different results. But, of course, the problem, as I've told you at the beginning, is that we're using for parameters alpha, beta, and sigma the maximum likelihood estimates. By the way, I didn't mention how you obtain those maximum likelihood estimates. It's very easy. For each animal, the likelihood function is just the product of the transition densities, because it's a Markov process. So it's very easy to compute. Transition densities between consecutive observation ages. And then, since the animals are independent, the likelihood for the whole flock of 18 animals is just the product of the individual animals' likelihoods. So it's very easy to obtain and very easy to maximize. Okay, but of course it's an estimate. Alpha, beta, and sigma is an estimate. The true values may be different. So we did the sensitivity analysis by using as baseline the maximum likelihood value, the one in the previous picture, and then you change it by half a standard deviation or one standard deviation. Okay, and you have 4 other points, red points, for the Gompertz model, and 4 other blue points for the Bertalanffy-Riches model. So with standard deviation is the standard deviation obtained approximately from the Fisher information matrix. Okay, so it's not exact again, but it's quite good. Okay, and you see the age, the optimal selling age, is still the same. Didn't change, except here it's 1.24 something instead of 1.25. That's when we change the parameter alpha, okay? But of course the profit changes a bit, because the parameter alpha, the maturity size, has a big influence on how the animal grows and the profit. So the expected profit varies a little bit, but the optimal age, which is the thing we can control, doesn't change. What about the parameter beta? You do the same thing for parameter beta and same feature, same thing applies. What about the noise intensity sigma parameter? Measures how intense the fluctuations are in the environment. It really has almost no influence on the expected profit. You see, the 5 points that were shown in the previous pictures here practically collapse. Well, there are still 5 points, but they are so close that you cannot see them apart. So in this, the parameter sigma has no effect on the optimal selling age and has almost no effect on the optimal expected profit. Okay. So you don't worry too much about the estimate of sigma, if it's very good or very bad. It's not really influential on this issue. It has an influence on the standard deviation. Now, what about if all the parameters change? Because they may be all wrong. So we did a sensitivity analysis with all parameters changing by simulating 1,000 parameter vectors using a Gaussian distribution with a mean value equal to the maximum likelihood estimated values and with a variance-covariance matrix equal to the empirical information matrix, empirical Fisher information matrix, which is a good approximation to the variance-covariance matrix. And of course, if for each age you have then a sample of 1,000 expected values, and you can plot the confidence intervals, corresponding confidence interval, confidence band for the curves, for the Gompertz model and for the Bertalanffy-Riches model in blue. So we have some confidence bands. But it's probably more interesting to look at this table. Optimal selling age, that's the true value, that is the maximum likelihood value, okay, assuming it's true. And these are the 1,000 sample mean and 1,000 sample standard deviation. You see, for the optimal selling age, the standard deviation is negligible. So it doesn't influence it doesn't change at all. Basically, the optimal selling age is practically fixed. As for the optimal expected profit, okay, the mean is good. It's very comparable to the true. But the standard deviation, of course, it shows up. It's 11.5 kilograms. But we've seen in the graph, of course, it changes a bit. That's for the complex model. For the bundle left reaches model, practically the same picture. Now, but we can plot it, okay? We plotted the optimal expected, the optimal selling age against the optimal expected profit for the 1,000 parameter vectors we have simulated. And you can see all the points fall in this line with a few exceptions. So the selling age is basically, with a few exceptions, 1.25, and even when it's not 1.25, it doesn't change that much. That's the maximum likelihood value for the expected profit, and of course the profit changes a lot. Okay, that's the value at which the farmers are selling the animals. This 1.16, and so a little bit below this one. That's for the bottom line reaches model, the same picture. So, in conclusion, it's about time, yeah. Yeah, just a couple of minutes for the conclusion. So we have done a body of theory in which we have modeled individual growth of an animal by using a very general and flexible class of stochastic differential equations, for which we have obtained the expected value and the variance of the, selling the expected for the selling price of the animal, for the cost of raising the animal, and for the profit. And we have obtained specific results also for two particular models, the complex model and Bertalanffy-Riches model, but of course we can do it for others. And the web tool was developed for farmers. It's very simple to use. The farmer puts the identity number of its animal. From the database, immediately has all the information is available on the different weights of the animal along its lifetime. And it has a curve for prediction. It can change parameters. It can add new information. And the projection for the curve of the expected value is made, and the optimal value is obtained. And you can even say, well, but I don't want to sell the animal that day because it's not convenient, it's a Sunday or something. So I want to sell it one day before, one day after. How much do I get? You can do that too. Or maybe he wants to join two different animals and sell them together instead of selling one day and the other 2 days later. Okay. So we applied it to a real case. Actually, we applied to two real cases, Myrtle-Angle breed and Alencena breed, but I've shown you the Myrtle-Angle breed case. Obtaining again the distribution of the results I've mentioned, expected values and variances of the profit, and we have also obtained the optimal selling age. As I've told you, the farmers are selling the animals slightly earlier, but not that much, so we have a little loss. And we also performed the sensitivity analysis to show how sensitive are the results to the parameter values, because we don't know the true values, okay? Well, we have actually we show that the parameter values have a mild influence on the expected profit, but have no influence, or almost no influence on the optimal selling age. That's the thing we can control. And the parameter sigma doesn't have an influence at all, or minute influence. So there's some references. This basic idea comes from Garcia some years ago. We applied that for the first time. This idea of using stochastic differential equations to individual growth was due to Garcia, but he applied to trees, not to animals, okay? But not really different. The main result, the main things I have presented today come from this paper here. Well, not the statistical stuff is spread, so other papers. But the main thing I wanted to say is that this technology of using stochastic differential equations certainly is much better than the classical regression technique, which has several flaws. And probably it wasn't used because stochastic differential equations is not in the mainframe of traditional researchers in this field, but it can be applied very easily. And all the artillery, even statistical artillery, can be done. We have also used mixed models. in which alpha and beta may vary according to genetic values. We have it, well, it's not yet on the web, on the computer tool. It's almost there, but we have results already. I didn't show you today. They're not published yet. How the parameters alpha and beta may vary with the genetic values of the animals. And in the database, the animals have genetic values. So you can use not a general alpha or a general beta parameter, but use an alpha and beta appropriate for that particular animal because you know its genetic values, or at least you have an estimate of its genetic value. You may say, well, if the animal is young, and it is, you probably don't know genetic values of growth or something like that. You don't. But the animal has relatives. And from the information on those relatives in the past, you can get an estimate of that animal. And the database allows you to do has that information too. Okay. So, merci beaucoup. Thank you very much for your attention. And also thank you to the sponsors of this research.